All right, let's dive into something super cool today, CNC machines. Now, you might have heard this term thrown around, especially if you're into making things, engineering, or even just cool gadgets. CNC stands for Computer Numerical Control. That sounds a bit fancy, doesn't it? But trust me, the basic idea is pretty straightforward. Think of it like a super smart, super precise robot that can cut, carve, shape, or even print materials. It doesn't get tired, it doesn't need a coffee break, and it follows instructions perfectly every single time. We're talking about machines that have totally changed how we build things, from tiny, intricate parts to massive airplane wings. It's a revolution, folks. A quiet one happening in workshops and factories all over the globe. So what does computer numerical control actually mean in plain English? Well, computer is easy enough. There's a computer brain telling the machine what to do. Numerical means it uses numbers. These numbers are like a secret code, a set of coordinates and instructions that guide the machine's movements. And control means this computer using these numbers controls the tools. It could be a drill, a laser, a plasma cutter, or even a 3D printer nozzle. The machine moves these tools with incredible accuracy to shape a piece of material, like wood, metal, plastic, or foam, into a desired form. It's like having a master craftsman who can repeat their best work flawlessly thousands of times. These machines aren't just one type of beast either. There's a whole family of them. You've got CNC mills, which are like super-powered drills that can move in multiple directions to carve out material. Then there are CNC lathes, which spin a piece of material while a cutting tool shapes it, perfect for making round things like shafts or custom bolts. We also have CNC routers, often used for wood or softer materials, great for signs or furniture. And don't forget CNC plasma cutters that slice through metal with a jet of hot plasma, or CNC laser cutters that use a powerful laser beam. Each one is specialized, but they all share that same core principle: computer-driven precision. The beauty of CNC is that it takes a digital design, something you create on a computer, and turns it into a physical object. Imagine drawing a complex shape on your screen, and then with a bit of programming magic, a machine carves that exact shape out of a block of aluminum. That's the power we're talking about. It bridges the gap between the virtual world of design and the real world of tangible things. This technology has opened up possibilities that were just science fiction a few decades ago, allowing for complexity and precision that human hands alone could never achieve consistently. It's truly a cornerstone of modern making. So how do these CNC machines actually work their magic? It all starts with a design. This design is usually created using CAD software, which stands for Computer-Aided Design. Think of it as a super sophisticated digital drawing board where engineers and designers can create two-dimensional or three-dimensional models of whatever part they want to make. They can specify every curve, every hole, every dimension with incredible detail. This digital blueprint is the very first step in bringing an idea to life with CNC. It's the master plan that the machine will eventually follow. This initial design phase is crucial because the machine will only be as good as the instructions it's given. Once the design is locked in, it needs to be translated into a language the CNC machine can understand. This is where CAM software comes in. CAM stands for Computer-Aided Manufacturing. The CAM software takes the CAD model and figures out the best way to actually make the part. It plans the tool paths. That's the exact route the cutting tool will take. It also decides things like how fast the tool should move, how deep it should cut, and which tools to use if the machine has an automatic tool changer. This process generates a special set of instructions called G-code. G-code is the common language for most CNC machines, filled with coordinates like X, Y, and Z positions and commands. Now, this G-code is loaded into the CNC machine's controller. The controller is essentially the brain of the machine. It reads the G-code line by line and translates those numerical commands into electrical signals. These signals are then sent to the motors that drive the machine's moving parts. We're talking about very precise motors, often servo motors or stepper motors, that can move the machine's axes, typically X, left and right, Y, forwards and backwards, and Z, up and down, in tiny, controlled increments. Some more advanced machines even have 5 or more axes for incredibly complex shapes. It's like a robot orchestra conductor, ensuring every part moves exactly when and where it should. As the motors move the machine's axes, the cutting tool, which is attached to a spindle or tool head, gets to work on the raw material.
This material, often called a workpiece, is securely clamped down to the machine's bed. Whether it's a drill bit, an end mill, a laser beam, or a plasma torch, the tool follows the programmed path, removing material bit by bit, or adding it in the case of 3D printing until the final shape is achieved. Many machines also have feedback systems like encoders that tell the controller exactly where the tool is at all times. This ensures that the machine is actually doing what it's told, making adjustments on the fly if needed. It's a closed loop of command and verification, leading to amazing accuracy. Let's peek under the hood, metaphorically speaking, and look at the key components that make up a typical CNC machine. First and foremost, as we've touched on, is the Machine Control Unit, MCU, or the controller. This is the computer brain, the central nervous system. It's where the G-code program is stored and processed. The MCU interprets these complex instructions and then sends out precise electrical signals to the drive system. Modern MCUs are incredibly powerful, capable of handling very complex geometries and high-speed operations. They often have a user interface, like a screen and keypad, allowing an operator to load programs, monitor the process, and make adjustments. Next up, we have the drive system. This system is responsible for moving the machine axis as directed by the MCU. It typically consists of drive motors, lead screws, and ball screws. The motors, usually servo or stepper motors, provide the actual motion. Servo motors are great because they have feedback mechanisms telling the controller their exact position, which allows for very high accuracy and correction of any errors. Stepper motors are simpler and move in discrete steps. These motors turn precision screws, like ball screws, which convert the rotational motion of the motor into smooth, linear motion along the X, Y, and Z axes. The quality of these components directly impacts the machine's precision and speed. Then there's the cutting tool and tool holder system. The cutting tool is what actually does the work of shaping the material. This could be anything from a tiny drill bit for intricate holes to a large face mill for flattening surfaces or a laser nozzle. These tools are held in a tool holder, which is then attached to the machine's spindle. The spindle is a rotating shaft powered by its own motor that spins the cutting tool at high speeds. Many advanced CNC machines feature an automatic tool changer, ATC. This is like a robotic arm with a carousel of different tools. When the G-code calls for a different tool, the ATC automatically swaps it out, saving a huge amount of time and allowing for complex jobs with multiple operations to run unattended. Finally, we can't forget the machine bed and work holding system. The machine bed is the sturdy flat surface where the workpiece, the material being machined, is placed. It needs to be incredibly rigid and stable to absorb vibrations and ensure accuracy. The workpiece itself must be held securely in place so it doesn't move during the machining process. This is done using various work-holding devices like vices, clamps, or custom fixtures. If the workpiece moves even a tiny bit, the part could be ruined. So, a solid bed and reliable clamping are absolutely essential for getting good results. These core components, working in perfect harmony, are what give CNC machines their incredible capabilities. The journey from a simple idea to a finished part using CNC technology is a fascinating process, a true blend of digital design and physical creation. It all begins in the mind of a designer or engineer. They have a concept, a problem to solve, or a component to create. This initial idea is then translated into a precise digital format. This is where computer-aided design, CAD, software shines. Using CAD, the designer meticulously crafts a two-dimensional drawing, or, more commonly these days, a three-dimensional solid model of the part. They define every dimension, every curve, every feature with exacting detail. This digital model is the virtual representation of the final product, the blueprint for everything that follows. Once the CAD model is complete and double-checked for accuracy, the next stage is computer-aided manufacturing, CAM. This is where the manufacturing strategy is planned. The CAM software takes the three-dimensional CAD model and helps the programmer decide how the part will actually be machined. This involves selecting the right cutting tools, determining the optimal cutting speeds and feed rates, how fast the tool moves through the material, and generating the precise tool paths the machine will follow. The CAM software simulates the machining process on the computer. allowing the programmer to catch potential collisions or errors before any actual material is cut. This simulation step is a huge time and money saver, preventing costly mistakes. After the CAM programming is done, the software outputs a set of instructions in a language the CNC machine can understand, typically G-code. G-code is a series of alphanumeric commands that tell the machine exactly what to do, where to move, how fast to move, when to turn the spindle on or off, when to change tools, and so on. Each line of G-code represents a specific action or movement. This G-code file is then transferred to the CNC machine's controller, often via a USB drive, an Ethernet connection, or even Wi-Fi. The machine operator will then set up the machine, loading the correct material and securing it to the machine bed, and loading the necessary tools into the tool changer if the machine has one. With the G-code loaded and the machine prepped, it's showtime. The operator starts the program, and the CNC machine springs to life. The controller reads the G-code line by line, translating the commands into motion. The axes move, the spindle spins, and the cutting tool engages the material, precisely removing or adding material according to the programmed path. The operator monitors the process, especially during the first run of a new part, to ensure everything is going smoothly. And voila! After the machining cycle is complete, what was once just a digital model on a screen becomes a real, tangible, precision-made part. It's a beautiful marriage of software and hardware. Section 5, way back when, the granddaddy of CNC numerical control. To really appreciate how amazing CNC machines are, we need to take a little trip back in time. Before CNC, there was NC numerical control. This was the first big step towards automating machine tools. The basic idea of NC started to take shape in the late 1940s and early 1950s. Think about the manufacturing needs back then, especially for complex parts in the aerospace industry. Making these parts by hand with manually operated machines was incredibly time-consuming, prone to errors, and required highly skilled machinists for every single operation. There was a real need for a way to make things more accurately and consistently. The pioneer of this technology was John T. Parsons. He was working on a project to manufacture helicopter rotor blades, which required very precise contours. He came up with the idea of using a machine tool controlled by numerical data. Instead of a human turning cranks and levers based on a blueprint, the machine would follow instructions encoded on a storage medium. The first NC machines used punch tape. Imagine a long strip of paper or mylar plastic with holes punched into it. The pattern of these holes represented the numerical data, the coordinates and commands for the machine tool. A reader on the machine would interpret these holes and control the machine's movements. These early NC systems were revolutionary for their time, but they were also quite clunky and limited compared to today's CNC. There was no computer brain in the machine itself, in the way we think of it now. The control was hardwired, meaning its logic was built into its electrical circuits. If you wanted to change the program, you had to create a whole new punch tape, which could be a tedious process. And there was no easy way to edit the program at the machine or simulate it beforehand. Debugging a program often meant a lot of trial and error and potentially wasted material. But despite these limitations, it was a massive improvement in precision and repeatability over purely manual methods. The development of NC technology was heavily driven by the US Air Force, which saw its potential for manufacturing complex aircraft components. They funded research at institutions like the Massachusetts Institute of Technology, MIT, which played a key role in refining NC technology. These early machines were big, expensive, and complex, mostly used in large aerospace and defense companies. But the seed was sown. The idea that a machine could be controlled by programmed instructions, rather than direct human manipulation for every move, was a game changer. This laid the essential groundwork for the much more powerful and flexible CNC systems that would follow with the advent of affordable computers. Section 6, the big leap, how CNC became the star player. The transition from NC numerical control to CNC computer numerical control was a truly transformative moment in manufacturing history. The big difference, as the C for computer suggests, was the integration of computers directly into the machine control system. This happened gradually as computers became smaller, more powerful, and crucially more affordable, starting in the late 1960s and really taking off in the 1970s and 1980s. Instead of relying solely on hardwired logic and punch tape, machines started to incorporate mini-computers and then microprocessors. This added a whole new level of intelligence and flexibility right at the machine. With an onboard computer, the machine's program, the G-code, could be stored in the computer's memory. This meant programs could be easily edited right at the machine without needing to punch a new tape for every little change. Operators could tweak speeds, feeds, or coordinates on the fly. The computer could also perform more complex calculations, allowing for smoother movements and more sophisticated machining strategies. This was a huge leap forward in terms of usability and efficiency. The reliance on fragile, cumbersome punch tapes began to fade, replaced by magnetic tape, floppy disks, and eventually direct network connections for program transfer. The computer also enabled more advanced features. For instance, cutter radius compensation became possible. This allows the programmer to program the actual part geometry, and the computer automatically calculates the offset path for the cutting tool based on its radius. This simplifies programming immensely. Another key development was canned cycles. These are pre-programmed routines for common operations like drilling, tapping, or boring. Instead of writing many lines of G-code for each hole, the programmer could just call a single canned cycle with a few parameters. This made programming faster and less prone to errors, making the machines much more accessible. Furthermore, the computer interface allowed for better diagnostics and feedback. The machine could tell the operator if something was wrong, display the current position, or show the progress of the program. This made troubleshooting easier and improved the overall interaction between the human and the machine. The ability to simulate the toolpath on the machine's screen before cutting material also became a standard feature, further reducing the risk of costly crashes or mistakes. This integration of computing power directly into the machine tool is what truly revolutionized manufacturing, paving the way for the highly automated and precise systems we see today. It wasn't just an improvement, it was a fundamental shift in how things are made. Section 7, Why We Can't Live Without Them, CNC in Modern Factories. CNC machines are not just a fancy tool in modern manufacturing, they are an absolutely essential backbone. It's hard to imagine how today's complex products, from smartphones to jet engines, could be made without them. Their importance stems from their ability to produce parts with incredible consistency, precision, and complexity, often at speeds that manual methods simply cannot match. In a world that demands high quality, tight tolerances, and rapid production, CNC technology delivers on all fronts. It has enabled mass production of highly sophisticated components, which in turn has fueled innovation across countless industries. One of the biggest reasons CNC is so crucial is precision and repeatability. A CNC machine can produce thousands of parts, and each one will be virtually identical to the last within incredibly tight tolerances. We're talking about fractions of a human hair. This level of consistency is vital for quality control and for ensuring that parts fit together perfectly in complex assemblies. Think about a car engine with hundreds of moving parts. Each one needs to be made to exact specifications. CNC machining ensures this level of accuracy, which is simply not achievable consistently with manual labor, especially on a large scale. This reduces waste, improves product reliability, and ultimately leads to better products. Another key aspect is complexity. CNC machines, especially those with 5-axis capabilities, can create incredibly complex shapes and geometries that would be extremely difficult, if not impossible, to make using traditional methods. This allows engineers and designers to be more innovative, creating parts that are optimized for performance, weight, or strength, rather than being limited by manufacturing constraints. Think of intricate turbine blades for jet engines or custom medical implants. These often feature organic flowing shapes that can only be realized through the precise multi-axis movements of a CNC machine. This ability to handle complexity opens up new frontiers in design and engineering. Finally, CNC technology significantly boosts productivity and efficiency. Once a program is written and tested, a CNC machine can run for long periods with minimal human supervision, sometimes even 24/7 in lights-out manufacturing environments. This drastically reduces labor costs per part and increases throughput. Automatic tool changes, pallet systems that automatically load new workpieces, and high-speed machining capabilities all contribute to this increased efficiency. This allows companies to produce more parts, faster and often at a lower cost, making them more competitive in a global market. Without CNC, the scale and complexity of modern manufacturing would simply not be possible. Section 8. The awesome advantages why CNC machines rock. When you stack them up against traditional manual machining methods, CNC machines come out on top in so many ways. One of the most obvious and impactful advantages is enhanced precision and accuracy. As we've talked about, these machines are guided by computer programs and precise motors, allowing them to make cuts and shape materials to incredibly fine tolerances, often measured in micrometers. This means parts are made exactly as designed every single time. This level of accuracy is critical for industries where even the smallest error can have big consequences. Like aerospace or medical device manufacturing, it ensures parts fit together perfectly and perform as intended. Another huge win for CNC is consistency and repeatability. Once a program is dialed in and proven, a CNC machine can produce hundreds or even thousands of identical parts without any deviation. A human machinist, no matter how skilled, will always have some slight variations from one part to the next, especially over long production runs. Fatigue, distractions, or even just a slightly different feel can lead to inconsistency. CNC machines eliminate this human factor, ensuring that the last part off the line is just as perfect as the first. This is vital for mass production and for maintaining high-quality standards across the board. Then there's the increased productivity and speed. CNC machines can operate much faster than manual machines, and often for longer periods. They don't need breaks. And with features like automatic tool changes and pallet systems, they can run with minimal human intervention, sometimes even unattended for entire shifts. This means more parts can be produced in less time, significantly boosting output. High-speed machining techniques, optimized tool paths generated by CAM software, and powerful spindles all contribute to faster cycle times. This efficiency translates directly into lower production costs and quicker turnaround times for customers. Lastly, let's not forget complexity and flexibility. CNC machines, particularly multi-axis ones, can create incredibly complex shapes and intricate details that would be nearly impossible or prohibitively expensive to produce manually. This opens up a world of design possibilities for engineers. Furthermore, CNC machines are very flexible. Changing from one job to another can be as simple as loading a new program and perhaps changing the tooling or work-holding setup. This makes them ideal for producing small batches of custom parts, like prototyping or bespoke manufacturing, as well as large production runs. This adaptability is a massive advantage in today's fast-paced, ever-changing manufacturing landscape. Section 9. Who's using these marvels, CNC, in different fields? The reach of CNC technology is incredibly broad. It's not just confined to giant factories making airplane parts, though that's certainly a big one. The aerospace industry relies heavily on CNC machining for producing high-precision components like turbine blades, engine parts, structural elements for aircraft frames, and missile components. These parts often involve tough-to-machine materials like titanium or superalloys, and they demand the utmost accuracy and reliability because lives depend on them. CNC provides the capability to machine these complex, critical components to the exacting standards required. It's truly indispensable for modern flight. Then you have the automotive industry. From engine blocks and transmission parts to molds for dashboards and body panels, CNC machines are everywhere. They're used for rapid prototyping of new car designs, allowing engineers to quickly create and test physical models. They're also used for mass production of components, ensuring that every car coming off the assembly line has parts that fit perfectly and perform reliably. The ability to produce complex molds with CNC also means car interiors and exteriors can have more sophisticated and aesthetically pleasing designs. The precision helps in making engines more efficient and cars safer. The medical field is another huge beneficiary of CNC technology. Think about custom orthopedic implants like hip or knee replacements. These need to be tailored to individual patients for the best fit and performance. CNC machines can create these highly personalized implants from materials like titanium or medical-grade plastics, with incredible accuracy based on CT scans or MRI data. Surgical instruments, dental crowns and bridges, and components for complex medical equipment like MRI scanners are also frequently manufactured using CNC. The precision and ability to work with biocompatible materials are absolutely critical in these life-saving applications. And it doesn't stop there. The electronics industry uses CNC for making precise molds for plastic casings of phones and computers, and even for drilling tiny holes in printed circuit boards or PCBs. The woodworking and furniture industry uses CNC routers for intricate carvings, custom cabinetry, and unique furniture designs. Even artists and hobbyists are getting in on the action with smaller, more affordable desktop CNC machines to create sculptures, signs, and custom parts. From large-scale industrial production to small custom shops, CNC machines are empowering creators and manufacturers across an amazing spectrum of applications, making things better, faster, and with more complexity than ever before. Section 10. So what's the big deal? Wrapping it all up. So after all this talk about computers, motors, G-code and amazing precision, what's the real takeaway about CNC machines? Well, the big deal is that they have fundamentally changed the way we make almost everything. They've taken manufacturing from a largely manual, skill-intensive craft to a highly automated, precise and incredibly efficient process. This isn't just a small improvement, it's a revolution that has touched nearly every industry you can think of. These machines are the unsung heroes working behind the scenes, churning out the parts that make our modern world function, from the tiniest screw to the largest aircraft wing. The core magic of CNC lies in its ability to translate digital designs directly into physical objects with astounding accuracy and repeatability. That link between the digital CAD model and the tangible finished part is incredibly powerful. It means designers have more freedom to create complex and optimized shapes, knowing that a machine can actually produce them. It means manufacturers can produce high-quality goods faster and more consistently, which ultimately benefits all of us as consumers. The precision reduces waste, the automation increases productivity, and the ability to handle complexity drives innovation forward in leaps and bounds. Think about the journey from those early clunky NC machines reading punched tape to the sophisticated multi-axis CNC machining centers we have today, often integrated into fully automated production lines. It's been an incredible evolution, driven by advances in computing, software and material science. And it's not stopping here. We're seeing trends towards even smarter machines, more intuitive programming, integration with artificial intelligence for process optimization, and the use of new materials. The future of making things is definitely going to be even more automated and even more precise thanks to the ongoing development of CNC technology. In essence, CNC machines are a testament to human ingenuity. They represent our ability to create tools that extend our own capabilities far beyond what was previously imaginable. They empower us to build a more complex, more efficient, and ultimately a more advanced world. Whether you're an engineer, a designer, a hobbyist maker, or just someone curious about how things are made, understanding the basics of CNC gives you a real appreciation for the incredible technology that shapes our daily lives. They are, without a doubt, one of the cornerstones of modern manufacturing, and their impact will only continue to grow. Pretty amazing stuff, right?